Hello and welcome to VHDL Concept 3, Combinational and Sequential Logic. We're also going to be covering process blocks in this video, and this will allow you to implement combinational and sequential logic in VHDL. So first we're going to get started using Logisim. We're just going to model the circuit that we're going to represent in VHDL. In Logisim, you can download this on the internet. It's a free tool to represent combinational and sequential logic circuits. It's pretty nifty. Anyway, we're placing a flip-flop, an OR gate, an AND gate, and an XOR gate. We're going to connect them up. We're going to have 4 inputs in this design, and it's going to be registered. So it's going to go through the D flip-flop and 1 output, and the clock also. The clock is an input. So this shows you the basic functionality of the circuit that is going to be coded up in VHDL. It's pretty simple, just 1 register, 3 logic gates, and there's not much more to it than this. Also, we're going to do a test bench in this video as well. So we're going to do a fairly exhaustive test on this circuit. There will be 2 components, a module description and its corresponding test bench. So if you don't know how to do this in Vivado, you can create a new project. We're going to start from the beginning, create a new project. Let's create a new RTL project, select some silicon. I'm using the Xilinx board, so I'm just loading that preset. Click on Finish. You may not have a Xilinx board or a Z board. Click on whatever gets your IDE up and running and follow along. So we click here. When you create a new design source, give it a name. And just click Finish. This window will pop up. No, we don't need to specify the ports. We're going to do that shortly. So dismiss that window. Double click on your module. I'm just deleting some of the auto-generated comments that Xilinx produces. So this is our module, C, C, and FF. We are going to give it the ports. We have 4 data input ports, A, B, C, and D, as in standard logic. We have a clock input, which is also standard logic, and we have an output. We're going to call it Q as out standard logic. The input to the flip-flop is going to need its own signal. And the reason for this is the output, our Q, can't be driven directly by the process. It must be driven by a signal. So remember that, signal. We also need a flip-flop input. This will simplify the combinational logic going into the flip-flop. You'll see this shortly. So these are two process blocks that are being coded. One is sequential and the other is combinational. Notice the sequential name. This is just a naming convention, so you can name that whatever you want. I've decided to name it sequential, followed by colon process. This tells VHDL it's a process, parentheses clock. So this clock drives the process. Whenever clock changes, this process block is executed. And we're going to put sequential logic in here. You'll see that shortly. So if rising edge, this is a VHDL construct, clock. So if that clock signal is rising, then we're going to do stuff. And if it's not, we're going to do something else. So I'm going to make an error in this code. You do not want to do this. Do not make this mistake. The mistake of trying to drive the output directly. And you'll see that shortly. On the combinational process block, we have 4 inputs, A, B, C, D. Whenever those change, any one of those signals changes will cause that process block to execute in the simulation on the combinational one. Okay, so I'm going to attempt to drive the Q output directly. So we're going to drive it from the flip-flop input. Again, this is a mistake. You cannot do this. Now in Verilog, you would be able to do this if you have an output register. The Verilog compiler would notice it's a register. This will throw an error momentarily. So the idea here would have been simply to drive the Q signal whenever the clock has a rising edge. Otherwise, we send the signal back to itself. So that would create a register. We're telling the compiler to create a register. So take note of that. We don't want to do that. I'll show you how to correct that in a minute. Now for our combinational process, we're going to look at our logic. So again, we had 2 input gates with each 2 inputs. We had an AND gate with inputs A and B, and we had an OR gate, inputs C and D. These were both XORed together, and that was the input to our flip-flop, which is now a flip-flop input signal we've designated, and it's being changed in one process. You don't want multiple processes driving multiple signals. Things get very confusing and messy. You may have a simulation error. So just keep them separate. And we're going to go ahead and try to compile this, and we're going to get an error thrown at us. Just breaking these sections up so it's clear. Again, these sequential and combinational processes are separate. This keeps the code clean. You don't want multiple signals driving multiple signals in your design. So compiling this design, and we get this error. And you don't want this error. It's not good. So to get rid of this error, we have to go to our culprit, which is over here, Q. The output is driving itself, but of course that is just an output. So what we're missing is an intermediate signal. Let's add an intermediate signal. Flip-flop out, and it's a standard logic. And this will be used to drive Q. So there are wrong ways to do that. And one is to assign Q the signal that we just created. So this won't work either. Now we're outside a process block with the flip-flop out, and we're assigning Q to that signal, and this won't work either. The problem, of course, is Q is being assigned a value inside a process block, and it is also an output in the port list. So what we need to do is assign our flip-flop out signal a value. So instead of Q in our sequential process block, let's put flip-flop out and assign flip-flop out our Q value, which we've done at the bottom, but our sequential process block still needs some attention. So if rising edge clock, then flip-flop out becomes flip-flop input. Otherwise, flip-flop out will be equal to flip-flop out, and that's what we're doing right now. The little cut and paste action. And let's assign our output signal the flip-flop out intermediate signal and compile this again. And it should run without any problem. So this is our RTL schematic view. Again, I'm using Vivado 2015.2. It's a tool by Xilinx. And that looks pretty familiar. We have a clock going into our flip-flop. We have 4 other inputs, 2 input AND gate and a 2 input OR gate, both of which those outputs are feeding into an XOR gate, which is going into our flip-flop. So we're going to add a test bench. Every design needs a test. We're going to call it TB, CC, and FF. Go ahead and click Finish. So again, I'm just going to go ahead and delete the comments that were auto-generated by Vivado. And this will be our test bench. Okay, remember the test bench does not have any ports. It's not something that is instantiated. So keep that in mind. What we do have, however, are internal test signals. And we have components that are added. And we also have a unit under test, followed by our test signals, which we drive. So let's go ahead and make our test input signals. These are our test bench signals. You can call them whatever you want. It's useful to call them something that is familiar. So I like to use an _T to designate test signals and just use the same signal names as the unit under test has. So we have A of T, B, T, C _T, and D _T. Standard logic. And we also have a clock signal as our test clock. And that's it. It's just the signals from the port list of the entity. And that's all you need. Here's our output signal. You can also add variables in your test bench, and we're going to actually do that in this video. But first, let's add a test bench component. So go back to your module or entity and just copy the entity name and port list, just like this. Copy that over to your test bench just under architecture in this section and above begin. You want to rename it as a component, not an entity. So instead of entity, put component, and it needs an end component. If you don't have these elements, it will not compile, it will throw an error. And it's going to be frustrating. You will have a bad time. Okay, we need a unit under test. We are telling VHDL that we are testing. Well, we're instantiating a component is what we're doing, and we're giving it a name. The name is UUT. You can call it whatever you want. So use the syntax below. We have a port map, and just place those signals into your instantiated component. Notice how it follows the same ordering as those listed in the entity under its port. So we have signals, we have a component in our test bench, and we've instantiated it. So we're going to have another process block. You can give it any name you want. I'm calling this one test bench process, colon. We have a process. Notice there is no argument in the process. Before we had arguments such as clock and A, B, C, and D in our entity. So this one doesn't have those. And there's something special about this. The special thing about this is without arguments, we can use wait statements. So we can wait for 5 nanoseconds, drive the clock T, our test clock, high, and then we can wait for another 5 nanoseconds and drive our clock low, again, our test clock. Now this is going to repeat forever and ever and ever. As long as the simulation runs, this will continue to cycle over and over again. If you wanted to stop it there, you could put a wait statement just above end process, and it would wait indefinitely. But since we want this clock signal to repeat, we're going to keep it going. Now we have a test input. I'm naming this test input. We have a process. Now this process block, the other one in the test bench, is going to take our test clock argument. So whenever that test clock fires, this process is going to increment. Well, it's going to execute. And we're using a variable. We're declaring a variable in this process called test inputs. It's going to be an integer, and we're initializing it to 0. And that's how you do it. With that syntax as shown above, you can obviously make it into whatever type of signal you want, but we're going to use it as an integer. Now, on the rising edge of the clock, our test input variable is going to be incremented +1. So it's going to retain its value and increment by 1. Now, for variables, you use colon equals. Signals is going to be the less than equal sign, but variables have a colon. So remember that. It's useful information. So the trick is, it would be nice if we could assign our test signals the value of this integer. Now, VHDL is strongly typed, so we just can't assign it without casting it. We're going to show you how to do that momentarily. So we're creating a new signal, signal ABCD underscore T. This is going to be a standard logic vector, 3 down to 0. So it's going to be made up of 4-bit components. So we're going to go ahead and drop that signal down here. So whenever the clock changes, this process will fire, our test input process. If clock T is rising, then this section of the process is going to be executed. Our ABCD underscore T will be assigned our value of our test inputs, which is that variable, which is going to continuously increment. Notice the casting. We have to cast it to unsigned. We have to designate it's 4 bits wide. And then we have to cast it again to standard logic vector. So there's always this casting going on. There's 2 stages of casting between integers and standard logic vectors. You have to use this format. Now each of the test signals can be assigned 1 bit of our A, B, C, D underscore T, standard logic vector. We're just going to give it some arbitrary numbers. 3, 2, 3, and 3. See if this will compile. We're going to go ahead and click on Simulate. Run simulation, and nope, it does not run. So we forgot to do something pretty basic here. We used library constructs, but we did not use the library, so we're not referring to the library at the top of our test bench. And we really need to do that. We need to include our library. So we have IEEE standard logic 1164.all, but we are missing the library that has the constructs for arithmetic. So what we're going to do is add the numeric standard library, and that has constructs for arithmetic that will allow us to use plus and minus, we can multiply and divide, and do all sorts of interesting things. You can take a look at that library if you would like to see what's inside. There are some good resources online. So let's go ahead and run the simulation. And it is functional. Looks like it is working. So our test bench compiles without error. Our entity, or module if you prefer, also compiles. Let's zoom out a little bit. Of course, we begin the simulation uninitialized. And once the data is pushed through the flip-flop, we get an output on Q. So this is not reflective of an exhaustive test. Our test signals, A of t, was assigned to the 3rd bit of our integer that is incrementing. B of t was assigned to the 2nd. C of t and D of t were not assigned to 1 and 0 respectively, but they are now. So let's go ahead and run the simulation again. And we should get a pattern that looks more like binary coded decimal, with D toggling the most frequently. Let's go ahead and take a look here. We zoom out a little bit. And there you go. That is our fairly exhaustive test. Now, exhaustive test means every possible combination of inputs is tested. And we're running through every combination of inputs. It's fairly easy with one flip-flop. If you have multiple flip-flops, things start to increase in complexity. For exhaustive testing, as you would have to drive one flip-flop high, perhaps the other one low, say they were cascaded, and then you'd run through every possible combination, and then you would repeat the test with maybe the first one being high and the second one being low, and then you would repeat the test again with both of the flip-flops high, and you might repeat the entire test again with both of the flip-flops low. So you have a massive amount of complexity, but we are not going to explore that. This is just a simple VHDL tutorial. But anyway, that gives you a fairly decent idea. I'd recommend functional testing for your modules, not exhaustive testing at this stage. You just want to make sure it works as expected. Does it reset? Does it initialize? Are the outputs what you would expect? And so on and so forth. So here's our, once again, our entity. This is the code for it. A moment ago, we were just looking at the test bench. And that is pretty much it as far as combinational and sequential logic blocks go. Again, keep the sequential assignments separate from your combinational ones, and you shouldn't run into any problems. Anyway, thank you for watching. The next video in this series will be looking at state machines in VHDL.